The work here involves the use of state-of-the-art ultrasonic testing methods and finite element method numerical simulations for the purpose of assessing the integrity of pressure vessels with defects that have been detected actually a very long time ago. This involves the reversible hydropower plant by Nabashta, which has a water storage tanks made of high-strength low alloy steel NeoWell 50 with a wall thickness of 50 millimeters. And using the older, more conventional ultrasonic testing method, it was determined that it has some kind of defects inside of its walls. So, but despite that, it has been in operation for decades. But a couple of years ago, we decided to test it using some of the more modern methods for ultrasonic testing, like phased array and time of flight diffraction, which would give us an even better insight into the position and the dimensions of the defects. And we also decided to combine this with a couple of other approaches. The first step of which was finite element method to numerically simulate this defect depending on the dimensions determined by the ultrasonic testing. And later we also plan to include the fracture mechanic analysis. So this was a bit of an unusual problem from my perspective, since whenever I have to do simulations of welded joints, it's usually related to something that has gone terribly wrong. But here we were trying to use multiple methods to prove that defective pressure vessel can still operate after it has already been in exploitation for a very long time. Here you can see the pressure vessel in question with its parameters and dimensions. And of course, the working pressure. It was made, like I said, from a NeoWell 50 steel, and the welded joints were made using the EVB 65 electrode as the filler material. And like I said, the ultrasonic testing detected a defect inside of the wall, which was 75 millimeters long and 20 millimeters deep, but it wasn't a surface defect. It was located at the depth of 18 millimeters from the weld face. It was inside the welded joint and went down to 38 millimeters in depth. So we are not even sure at the moment if it was actually a crack, but we assume that because this is the worst case scenario, and we'll always work with that. If we could confirm its structural integrity with a crack, then it will also work with any other type of defects. As for the ultrasonic testing, it was performed in 100% scope along the 3 circumferential welded joints in accordance with the relevant standards that you can see here. And you can also see the equipment that was used by my colleagues, the USM36KSL Kraut-Kramer device. This was used for the first initial tests from some time ago, and now more ultrasonic testing were performed with, of course, state-of-the-art equipment. And here you can see a bit more detail about the phased array equipment that was used, of course, with all the relevant standards, the measuring area that you can see here, the transducers, and of course, the pressure vessel surfaces were covered by anti-corrosion protection from the beginning, which was something that also needed to be taken into account. Here, there's a lot of results from the ultrasonic testing. So just showing you some of these examples, especially since I wasn't the one who did these tests. But here you can see the advantages of the phased array. You can get a very detailed view of the defects with very accurately determined dimensions and the depth, length, and everything we needed. And also, we also use the time of flight diffraction method. And here you can also see an example of one of the results that were obtained, where you can clearly see the defects and all the relevant dimensions. So once we had a lot more detailed version of the defect, we decided to also first make a numerical simulation in Abacus using finite element method. We tried 2D models and 3D models, but we decided to stick with the 3D models because not only are they more representative, in this case, they were even easier to make, which is usually not the case. So we took a segment of the vessel where the crack was present, so we won't have to simulate the whole thing to make the calculation less time consuming. And here you can see the relevant parameters, the elasticity modulus, the Poisson's ratio, and the parent material and the metal tensile mechanical properties. The values you see here are true stress strain values, which are the requirement for such calculations in Abacus. And here you can see the model, the segment of the vessel itself with the boundary conditions that were initially defined as fixed on both ends, but later we decided to remove this one for more realistic results. And if you put, because the crack was located around here, so very close to the boundary conditions, and in that case we didn't get any results. That will correspond to the later solution that was adopted with a stiffener ring that was placed around the vessel. But for now, we worked with, just a second. We removed this boundary conditions, and here you can see the internal pressure of 77 bar, according to what we found in the documentation. Here you can see the finite element mesh. Here it was, of course, more refined with smaller elements. This is where you see where all of these yellow lines are. This is where the welded joint was actually located. We'll see that in more detail in the next of the images. We also created a model that didn't have this crack inside, just for comparison purposes, with the same geometry, same boundary conditions and everything. And here you can see the crack locations inside of the pressure vessel wall. And here there's a detailed view of the finite element mesh in this critical area where the welded joint was located. And here we have the stress state for the model without the crack, which was cut vertically. So you can also see the distribution along the thickness with values which are still within the safe zone, around 356 megapascals, because the yield stress of the material that was used in all 50s and the AB65, the lowest of the values was 560 something. So this is still safe. Now, and this is what happened when we introduced the actual crack. Here you can see that the stress concentration that it tips. It's important here to note that the crack did not propagate in length in any way. It had the same length as we initially defined, the 20 millimeter, or in this case, depth would be more accurate. It just slightly opened up along the transversal direction, and the maximum stresses were 563 megapascals, which are just around the yield stress, so the lowest yield stress of the materials, which corresponds well to what we already knew, that the pressure vessel can continue operating, because even if this was a crack, and we still don't know that, it still cannot produce stresses high enough to cause crack growth. This barely entered plasticity, and the values were very low, way lower than 1%, which is what we usually considered the lower limit before we start taking things seriously. So the presence of this crack-like defect did not have any adverse effects as confirmed by the numerical simulations and also by the ultrasonic testing. So there was pretty good agreement in terms that it can actually still operate, and already has been doing for quite a while. With I already mentioned the stress values. And of course, there was no plastic strain, no crack growth. So this is basically a brief overview of how we combined modern day ultrasonic testing with numerical methods to determine the structural integrity of a vessel in defect, so a very long exploited one. And for now, we had some pretty good agreement between the results. And in the future, we plan to also conduct a detailed fracture mechanics analysis in hopes that it will also confirm what we know. At some point, we would also like to take a more detailed look at the defect itself to see what might have caused it, and to determine for how long it can continue working. So thank you for your attention.